Now this little segment is to briefly investigate one of the more common notations that textbooks and physics books use for line integrals. So recall that we have our line integral to calculate work, which is the integral of the dot product of the force or vector field with the velocity of the curve with respect to t, and remember the c is the curve or the path through that particular field, and it could be 2 or 3 dimensions. So the notation that the book uses, we'll end up with in just 2 short steps, takes this notation we have here, line integral, and makes us recall what a velocity vector is. And the velocity vector is the derivative of the position vector or the curve with respect to t. All right. And if we distribute this dt as if it were a scalar, we end up with the following. Line integral force or vector field dot product dr. So this little abbreviation, it doesn't even look like it should be a dot product. What does d vector mean? But it's a shorthand. And shorthands are used when we have to do many problems, and it was very cumbersome to write it out every time. So the author is going to call this sort of the more common notation. But we're going to use this one as sort of what does a formula represent. So let's take it for a drive on an example. So we take the directions, evaluate the line integral for work given by the following information. So we have a vector field f of xy is y squared comma xy, and then we have the curve r of t, and that is the vector, simple vector, which happens to be a line 2t comma 3t, and we have a time interval from 0 to 2. So our job is just to determine how do we set up this integral for work and what it's equal to. So please remember that this is x and this is y, which we will use in this vector field for the vector field to be evaluated at only points on the curve. But we also need the velocity vector to investigate this. So velocity vector is going to be the vector 2 comma 3, the first derivative of those components. So let's set it up. Work equals the line integral from 0 to 2. Velocity is second, so we need the vector field at first. It says y squared. Y is 3t. Then the second component is x times y. X is 2t. Y is 3t. There's your force or vector field. Dot product velocity vector, which is 2 comma 3 with respect to t. So that's what we're going to evaluate. So let's do that really fast. So the dot product would be 9t squared multiplied by 2 would be here 0 to 2. So that would be 18t squared. And then this is 6t squared times 3, which is 18t squared, which is the same exact as the first term. And we'll add those together next. We now have a scalar, not a dot product or a vector at all. So we're going to integrate from 0 to 2, 36t squared with respect to t. And this antiderivative is going to be equal to 12 times t to the third. Using the power rule only to do this. We don't need anything more powerful. From 0 to 2. 2 cubed is 8. 8 times 12 is 96. 0 cubed is 0. 0 times 12 is more 0. So we end up with a work equal to 96. We weren't given units, but perhaps the units are in joules if we were in a physics class. There you have it. Easy peasy.